Okay, so let me kind of now focus on these Moire materials, and also I'll there are many different aspects that one can talk about regarding these graphene Moire materials, but I'll focus on their band topology. Okay, that's one thing that we have been very interested in, and I'll try to argue that potentially they are important for understanding the physics of these materials, where it's clear that interaction effects are very important. And what really got people interested here was discovery of superconductivity and of these insulators that you probably cannot explain without strong interactions. And in fact, most of the interesting stuff occurs when the ratio of the interaction strength to bandwidth is very large, clearly a strong interaction regime. Okay, but we'll see that the understanding the nature of wave functions that are involved is actually important, and in particular, the topology of these wave functions may be important to understand all of the physics that's being seen. Okay, so one part of my introduction last time that I didn't quite complete is to talk just a little bit about the band structure of graphene, which many of you are very familiar with. But I just want to emphasize again a couple of points. So like the model we had last time, where we had hopping between this A and B sublattice of a one-dimensional system, graphene is sort of a two-dimensional analog of that. The dominant hopping is again between these two sublattices. There are two sites in each unit cell. I can label them A and B, and clearly A and B are different. They're not symmetry equivalent. One is kind of pointing up, the other is pointing down. There are two different sites, and predominantly you have hopping between the A and B sites. So these are also B sites. And you can write down a Hamiltonian. There's a 2x2 matrix Hamiltonian, and the dominant hopping is off diagonal. Okay, as before, A to B hopping, it has some phase factors depending on the wave vector as usual. And when you solve that problem, you end up getting these Dirac points that live in the two-dimensional Brillouin zone. Okay, so this let's write it in terms of Pauli matrices, and it's conventional to use sigma for these Pauli matrices. And the important thing to remember is sigma z is really just the sublattice A or B. Okay, and that's going to appear again in an important way when we talk about this twisted bilayer graphene. Okay, so there's a notion of chirality in the sense that we talked about before. If you write down the Hamiltonian, the simple tag binding Hamiltonian, everywhere actually for all wave vectors k, it has an x and y component. Only x and y sigma matrices are involved. It's off diagonal. There's no z component. Okay, and that's really because of this. You can say because of the chiral symmetry. There's the sublattice operator anti-commutes with the Hamiltonian. That's why sigma z itself is forbidden. Or you can take a more physical approach and say what we have is time reversal and inversion symmetry, 180-degree rotation symmetry. And again, when you see how that is implemented, it prevents the sigma z from appearing. So you have a two-dimensional vector. It lives in the plane. That's the vector that represents the Hamiltonian. And it can have vortices as you go around the Brillouin zone. Okay, it's just a vector. And in fact, the location of these vortices are really the Dirac points. Okay, so if you draw the band structure of graphene with the simplest hopping, it looks like this. There are two bands corresponding to the two sublattices, but they're not disconnected. Okay, unlike the one-dimensional case that we talked about, where you had these two disconnected bands and you have to tune something to get to a transition with the Dirac point. Here, the Dirac point is always there, but you have to search for it in momentum space, and it lives at these points, the k and minus k point in the Brillouin zone. Okay, so if you go there and expand the dispersion, it's linear in the deviation from those points, and it has these Pauli matrices coming along with it. Okay, the important thing again is you don't have sigma z. Sigma z would have been a mass term for this Dirac equation. Okay, if you're allowed a sigma z term, it would anti-commute with these matrices. The dispersion would be that of a massive Dirac particle. That's forbidden by symmetries, the symmetries we talked about. So you have a massless Dirac fermion. And the chirality, if you like, of these two Dirac fermions, let's say at k and minus k, all these other points are equivalent. They're up to some reciprocal lattice vector. Basically means they're the same in this periodic torus. These two Dirac points, they have the plus and minus sign coming over here if you simply expand. I think this is something to remember. We're going to contrast this with the band structure of this twisted bilayer graphene, where we'll again get two drug points. You'll be tempted to say, oh, it's a lot like graphene, but you'll get both of these will be plus signs, and that will make a big difference. Okay, so we can try to understand the stability of this band structure to additional interactions. What if added other couplings, other hoppings? Well, these Dirac points are kind of nailed down at these positions because of the threefold rotation of the crystal. Okay, clearly you can make a threefold rotation of this crystal. It's invariant, and that is what is spinning the Dirac points to these particular momentum. Okay, and now if you ask, how can I remove the Dirac points? How do I get, get rid of this, these band touchings? If I want to sort of separate out the bands, get an insulator, well, there are at least three ways you can think of. One of them is to break this rotation symmetry, 180-degree rotation symmetry. Yeah, and one way to do that is if you think of these sites, the A and B sites, as being chemically different. Okay, of course, in carbon they're the same, but if you had another material with the same structure, boron nitride, for example, boron and nitrogen forming the A and B sites, then you'd have a potential that's different on the two sites. That would show up as a sigma z term, right? Obviously, sigma z is sublattice. Potential would look like sigma z, and it would be essentially independent of momentum. Okay, it's just a zero wave vector object. So you'd have the same m at both of these Dirac points. Okay, and of course, because the chirality is different, these end up giving you different quantum Hall responses. So we talked last time how a Dirac fermion with the mass term in 2 dimensions gives you a quantum Hall response, but those two responses cancel when you have this kind of staggered potential, which is good because it doesn't break time reversal symmetry. Okay, so you cannot get a Hall effect, and you get a Hall effect from one Dirac point, the opposite one from the other one, and they cancel out. Okay, so that's one way to to break this Dirac point. There's another way which was discovered by Duncan many years back, which is to actually break time reversal symmetry. Okay, so you want to set up a situation where these two mass terms are opposite in sign. If you can do that, then the Hall effect coming from these two Dirac points will add. You'll get a Chern insulator. You'll get something with the Chern number. And the way to do that, he showed, was to have the second neighbor hopping with an imaginary coefficient. The imaginary term breaks time reversal symmetry. It's called the Haldane mass term. And that gives you another way to separate out the Dirac points. There's a third way for graphene, which you could think about, which is to break the rotation symmetry, C3. The Dirac points detach from their preferred locations. You can bring them together, and because they have opposite chirality, they will annihilate. And then you can separate out the bands. Okay, this, unlike these two, so in these two mechanisms, the tiniest mass term will give you a gap. In this third one, you need a finite strength of C3 breaking. You've got to kind of, these Dirac points have to travel across the zone and then annihilate. It's sort of qualitatively different mechanism from these two. Okay, but that's another option that you have. All right, so that's some basics of graphene. And now let's talk about the variant that we want to think about. This was the monolayer graphene that I just talked about, but now imagine you have two of these layers, okay, a bilayer, and then you twist it. Okay, and you twist it at some angle. I've shown a rather large angle. We'll be thinking about much smaller angles, but for you to look at it on this screen, it's actually easier to do it at this large angle. Okay, so we're going to be interested in structures like this, twisted bilayer graphene. This will you can kind of see that there is some superstructure that is developed. That's called the Moiré lattice, this system behaves effectively like there is a new crystal with the periodicity of this Moiré lattice, and the electrons are propagating, seeing that other potential, okay, seeing the potential of this other lattice. The thing that's really interesting about using graphene to do this is you're actually subjecting Dirac fermions to this periodic potential, okay, in a very particular way. That leads to some interesting effects. Okay, so you have this unperturbed Dirac cone of the single layer. There's another one because we have two layers, and I'm only looking at one of these K points. Okay, so I'm really focusing at one part of the Brillouin zone. There's another part It's kind of a mirror world where all of these are reflected, and you have Dirac points at the minus k point. Okay, but let me just focus on one pair of them, and this is the valley degree of freedom. So this is one valley that we're looking at, one flavor of the Dirac fermions. Okay, so once you have them and you do this rotation, they're slightly displaced in terms of their momentum effectively, and now the electrons tunnel between the layers. So these bands mix. For example, where they cross, they have the same momentum. When they tunnel, these two bands will mix and split. Okay, just like any pair of degenerate levels in quantum mechanics, they can split, and this will modify the band structure that you get. And if this modification is strong enough, which is what happens in this case for small angles, you will get some effective physics, some effective bands that live within this, that are produced by this Moiré lattice. Okay, so that's what we want to examine, how exactly are these bands created, and what is the nature, the topology of those bands. Okay, so it turns out that you will get these isolated bands very close to zero energy, and the experiments are really about exploring that little window of energy, and by gating, you can change the number of electrons that live inside that band. Okay, so you have a lot of control, which we usually don't have in solid state physics. You need chemistry to change the number of electrons. Okay, so just to kind of give you a preview of what we are going to find, that if you have a very small angle, around 1 degree, then you end up with a band structure that looks like this. Near zero energy, near where the Dirac points used to be, you see mirror Dirac points. Okay, there's a mini Dirac point that remains. This is all in the very small Moiré-Brillouin zone. So the Moiré structure is going to be a large-scale structure. So if you go back, do a Fourier transform, that means a small Brillouin zone. And inside the small Brillouin zone, you have something that looks like the original Dirac points. Okay, but we'll see there's a twist. There's a band that's isolated from other bands that just occupies energies near this neutrality. Okay, and it has a very small bandwidth. This you should compare against the bandwidth of graphene that's 1,000 times bigger than this. Okay, so everything is scaled by a large factor. This is the length scales we're talking about, tens of nanometers. That's where the length scale of this Moiré structure. Again, it's about 1 to 2 orders of magnitude bigger than the atomic length scales. Okay, so really there's a small parameter in this problem, which is the angle. Okay, and the natural units to measure angle are radians. So 1 degree is about 1/60th of a radian. The length scale is really the atomic scale divided by the small number. Okay, so compared to atomic physics, if you want to kind of compare to regular materials physics, all scales are going to be changed by roughly a factor of 1 to 2 orders of magnitude. Okay, so so one obvious question you may ask is, what is setting this angle? What's magic about this angle? Why is 1 degree special? And so there's a simple argument, which is essentially a dimensional analysis argument, which tells you how to understand this angle. Okay, so let me walk you through that argument. So this just is another picture that shows in momentum space what happened when you twisted these layers. Okay, so you had the original Brillouin zone, blue and red, corresponding to the top and bottom layer, and this is big. Okay, that is the fact that you're talking about atomic scale physics. So now you do this twist and you get another Brillouin zone, which is essentially the Brillouin zone of this Moiré lattice. It's rotated by 90 degrees compared to the original Brillouin zone, and it's much smaller, of course. But the projection of the original Dirac point survives into this new small Brillouin zone. And the other important fact is there's another partner Brillouin zone, the other valley. We'll always be talking about one valley. And these are essentially dynamically decoupled, okay? Because at least at the one particle level, unless you have some very large momentum transfer, you won't get from here to there, okay? Unless you have some really, some point impurity that can transfer a large amount of momentum, electrons kind of live within one valley or the other valley. Okay, so these are really like flavors of fermions that at the one particle level do not talk to each other. Okay, so just to give you an idea for this dimensional analysis, so when you have this Dirac points of the original graphene, they have some velocity, and there's a scale, energy scale associated with them, which is the velocity divided by the lattice scale, and that's tens of electron volts. So now you do this twist, and you have a separation between these Dirac nodes that's proportional to your angle. Okay, the larger the angle, the larger the separation. This is the momentum separation, and using the velocity, you can convert that into an energy separation where these bands cross. Okay, so just multiply by VF, and in EV, that is something like this, given the velocity of graphene. And now there's a natural scale for coupling between the two layers. Okay, so you just take two sheets of graphene, allow them to sit next to each other at their natural separation. There's a certain scale to the electron tunneling between the layers. That's known from bilayer graphene. That's this number, and you're trying to equate these two scales. Okay, when they balance, something can happen. Okay, you don't know for sure that it's going to give you this extremely flat band. But if the scales are really off, for example, if this angle is very large, this coupling is not going to do much to your band structure. You can sort of neglect it. It's only when the angle drops below this ratio, about 1 degree, that's interesting stuff can happen. It still remains to be seen if it does. Okay, so you can think of this roughly as follows. There's some time scale for the electrons to go between the layers. Okay, given the natural tunneling scale, it takes some time for an electron to tunnel between the layers, and it can also move within the layers. Okay, so you're looking for kind of a resonance. The time it takes to go from one Moiré lattice site to another, that should be comparable to the time that it takes to tunnel between the layers. That's when interesting stuff can happen. Okay, and that turns out to be at roughly 1 degree. Okay, so I already emphasized this U1, the valley conservation, which gives you a U1 symmetry. The charge number of electrons at each valley is separately conserved, in addition to the total number of electrons being conserved. Okay, because this is a large angle, a large momentum transfer. Okay, so of course, what was led to a lot of excitement was this the discovery of this Mott insulator. It's called a Mott insulator, essentially an insulator at certain fillings and flanked by superconductivity, which was very quickly reproduced. And I'll also mention some of the experiments, very interesting experiments, more recently, where people have observed a quantized Hall effect in a slight variant of the system. Okay, so there are essentially two families of these systems that are present, and it's kind of important to kind of highlight the difference between them. So one of them is this situation where we have these two layers of graphene twisted with respect to each other. And then there are more complicated systems. For example, you could have two bilayers. Okay, a bilayer of graphene on another bilayer, and they're twisted with respect to each other. This is what bilayer graphene looks like. So if you really look at the configuration a pair of graphene sheets would like to take, the atoms don't sit right on top of each other. Instead, they like to form the so-called Bernal stacked graphene, where one of the sublattices is at the center of the honeycomb, and the other one is beneath one half of the other carbon atoms. Okay, it's called Bernal stacked graphene. But then you can take two of these sheets and twist them with respect to each other and put them down. There's also a so-called trilayer graphene, ABC trilayer graphene on a substrate. And even this system, if it's put on certain substrates like boron nitride, you can end up losing this symmetry, this C2 symmetry, okay, just 180-degree rotation symmetry. Okay, so we're going to emphasize this symmetry. This turns out to be very key, and it seems like there's one kind of phenomenology associated with C2 symmetric systems, essentially the original Moiré graphene, and another associated with this set of systems where you break rotation symmetry. Okay, so either intrinsically or using a substrate. Okay, and in fact, this is where superconductivity is most commonly seen. And here in some of them, superconductivity has been seen, like this one and that. But we'll talk a little bit about this, more recent experiments as well, where the quantized Hall effect has been observed. Okay, so that's just to tell you it's not C2 symmetric. Okay, so let me just spend a few minutes before I get into more details about the band structure, why this band topology may be important, even to understand the interaction physics. There are really two different kinds of strongly interacting systems that we are familiar with in condensed matter. Of course, the cuprates, things like the cuprates, where you have very small bandwidth compared, or you have bandwidth comparable to the interaction strength. Um, and in those cases, you can sort of reduce the physics, many people believe, to a tight binding model, Hubbard model, right? So there are electrons sitting on sites, and they hop between the sites, and there's an on-site interaction. Okay, and there's another paradigm, which is the quantum Hall effect. Again, strong interactions do all kinds of interesting things over there. And here you have Landau levels. You have the analog of bands over here, or filling bands is filling these Landau levels. There's a difference between these two paradigms, and that's really the question of whether you can write down such a tight binding model. Okay, so the bands relevant for the cuprates that you fill partially are such that you can actually write down Wannier functions. You can write down localized orbitals that, if you think about hopping between them, will reproduce this band structure. Okay, not just quantitatively in terms of all of these wiggles, but also the wave functions will be reproduced. There's no way to do that for Landau levels. Okay, and essentially that's because the Landau levels carry a Chern number, like we talked about before. All the Chern, all the non-trivial classes in class A, where you have this Chern number in 2 dimensions, it's impossible to reduce that to Wannier functions. Okay, you cannot just write down some tight binding model that will capture just that one band. Okay, you could have additional bands that you could write down, models for, but that single band cannot be captured by some tight binding model. Okay, and that reflects the fact that you have interesting things like edge states and so on. And the way you go about solving this problem for the Landau levels is that you dispose of trying to write down a tight binding model. Instead, you work directly with the lowest Landau level wave functions. You project all the interactions into that lowest Landau level, and there's no kinetic energy. But the way the band structure makes itself felt is through the geometry of the wave functions. Okay, so it knows about the wave functions, knows about the band structure, although there is no dispersion. Okay, and the question that is kind of interesting to ask is this magic angle graphene, which is clearly a very strongly interacting system. It has a very small bandwidth, a large interaction strength. Which paradigm does it fall under? Okay, is it more like the cuprates, where we should find our Hubbard model and spend the next 20 years trying to solve that? Or should we think about it in terms of Landau levels, something like Landau levels, dispose with Hubbard models and so on, try to project interactions directly into this band and make progress? Okay, so that's really the question. And what I'm trying to argue is that there is some band topology associated with this system. That sense, it's different from the cuprates. Okay, so or these things where you can simply write down this kind of Hubbard model and kind of tee off from there. And it's going to be related, to summarize this in a physical way, it's going to be related to the fact that these two nodes that you have in the band structure have the same chirality. Okay, they descend from Dirac points from different layers with the same chirality. That's some form of band topology, which will obstruct us from writing this kind of tight binding model. Yeah, and another way to think about it, it's a sort of a sandwich of Landau levels. It's sort of, there's a Landau level and an opposite magnetic field Landau level sandwiched together. That's another way to think about this pair of bands. Yeah, and again, that's some sort of band topology, but the band topology is not as strong as in the case of the quantum Hall effect. It turns out that by writing down a few more bands, adding some few more bands that are essentially trivial, you can write down an extended Hubbard model with more sites than just these two orbitals. That gives you a description which is a bit like this physics. Okay, so in a way, it's somewhere in between. It has some level of band topology, but not of the kind which forces you to just work within the subspace. Okay, so I'll try to explain that as we go along, and that's kind of the sort of two parts of my talk. I'll try to give you a description of these bands in momentum space, and where you'll be able to see this topology. And towards the end, I'll tell you our work on trying to make Hubbard models, extended Hubbard models for them. So any questions at this point? Okay, that's a bad sign. But okay, so let me tell you a little bit about this continuum, this model where you try to solve for the band structure of this twisted bilayer graphene. Okay, so since this is a low energy phenomenon, you can approximate the band structure of the original graphene sheets by Dirac fermions. Okay, so this is sort of an interesting problem where you have Dirac fermions moving in a layer, and they're allowed to drop into the other layer and proceed. And there's also some periodic structure, which is this Moiré potential. Okay, and you can write out the Hamiltonian like this. So this is just the Dirac fermion part. There are two Dirac fermions, top and bottom layer. And the way in which this Moiré potential makes itself felt is through these transition matrix elements, okay, through the electron hopping between the layers. And its amplitude is modulated depending on where you are in the sheet, depending on where you are inside this periodic structure. Okay, so that's where the periodicity appears. This is going to give you a band structure. This is the individual layers, which are, if there was no coupling, this would just be the two Dirac fermions in the individual layers. Okay, so another thing I want to emphasize is that each of these entries are 2 by 2 matrices. Okay, there's sigma appearing over here. That's the sublattice. Okay, so remember, because there's chiral symmetry in each Dirac fermion, the sigma is just the x and y components of the sublattice matrix. Okay, and this is something that tunnels you between the layers. It also has some sublattice structure. Okay, so this tunneling matrix element you can write down in this sublattice basis. So just to be completely explicit, these indices over here are top and bottom layers, up and down. This is the top Dirac point, bottom Dirac point. Of course, we're looking at just one valley. There's another valley which has a similar equation. And this matrix over here is a 2 by 2 matrix, which tells you the tunneling between the two layers. If you're tunneling from A to A to B, B to B, and B to A. Okay, and there's some symmetry relating these two, for example, and these two are the same. Okay, so that's the setup of the problem, and this is the problem that was solved by McDonald and many other people. And it gives you a band structure, which I'll show you. But one interesting thing you could try to do is to exploit this chiral symmetry. Okay, and that's what we did in this work with Grisha. Was actually a student here, working with Igor and Sasha Polyakov. But he's, we've gotten interested in some of these condensed matter problems now. So he looked at this model, or he analyzed this model where you switch off the hopping between the layers, which correspond to the AA sites. Okay, the hopping which takes you from an A sublattice to another A sublattice, or B to B. Okay, so what you're left with is this A to B hoppings. Okay, so at this point, this is completely, a theorist, experiment, if you like, what happens when you do this. But we'll see there is some physical reason to believe these hoppings are weaker than these ones. Okay, so, but anyway, let's try this. And let me just give you a picture of what these two kinds of hoppings mean. So you have these, this is a pair of sheets twisted with respect to one another. So let's say I centered them on this honeycomb site and twisted them. So you see that these are very close to one another. So here the hopping will be between the A and A site. So this is an A site and that's another A site. This is called the AA regions. Okay, so there's one hopping matrix element there. There are also other regions which are AB regions. Okay, so you see there's an up pointing site and a down pointing site. And they are kind of occluding each other over here. This is called an AB region. So these AA regions form a triangular lattice, as you can see. That's the Moiré lattice. But the AB regions, they form a honeycomb lattice. Okay, if you just pick out these regions. And there's also another lattice sitting there that will show up later, which is sort of at the midpoints over here. There's a Kagome lattice as well. And those will also be important sites in this geometry. Okay, but for now we're asking whether this this coupling versus that one. What if you just switch off these couplings and only allow for tunneling over here? Okay, so one physical reason why you may expect this to be larger is that this is really looks like the Bernal stacked graphene. right? That's the arrangement graphene likes. So actually the sheets get a little closer to each other over there. There's a slight enhancement of the tunneling over here. So you'll see this model, this theorist model is actually somewhat closer to reality than you might expect, right? But when you do that, this entire problem has chiral symmetry. Okay, everything is only hopping from A to B. Okay, the original hopping in the graphene sheets, the hopping between the graphene sheets as well. Okay, and we're going to exploit that chiral symmetry, and it'll give us some very simple consequences. Very simple, some simplification. Okay, so there's a matrix, which is just the sublattice matrix, which will anti-commute with the Hamiltonian. Okay, so once you do that, let's look at what our problem looks like. So now, because you have this chiral symmetry, I've shuffled the indices around. I'm going to write my Hamiltonian primarily in terms of this AB sublattice spaces, and everything's off diagonal. Right, that's chiral symmetry. And the entries over here, if you look at it, this is again a 2 by 2 matrix, now in the up and down bases. Okay, and there's a derivative over here, which is coming from the Dirac equation. And I've combined the x and y coordinates together to give me a complex analytic derivative, okay, d by dz bar, I guess. So I have that, that's the Dirac part. And then you have this coupling, which is the tunneling between the two layers, just the AB part of the tunneling. Okay, so this Hamiltonian, you can actually view it as Dirac fermions experiencing a non-abelian gauge field. Okay, actually an SU2 gauge field. It's a static gauge field. It doesn't fluctuate in time. But you know, the way to think about it, of course, is that there's this up-down 2 by 2 matrix. There's the Dirac part, which is the identity in this space, and then there is this, which is off diagonal. It'll involve both the x and y Pauli matrices in the up-down basis. Okay, so it's non-abelian. It has at least 2 components of this up-down matrix, and it will turn out this non-abelian nature is very important. Okay, so we'll see that if you find a deformation of this model where that becomes abelian, you don't get these magic angles. And actually, we don't know why, but yeah. So this, if I expand this out, you have different. This is like a tau plus and tau minus. You can write it as a non-abelian gauge potential with an x and y component. Okay, so now if you look at the band structure of this model, and I'll show you this in a little more detail, and you can compare it with the model I talked about before, which is due to McDonald and Company, where they have equal coupling between the AA and the AB parts. Okay, so there are 2 options. You can either switch this one off, which is what we did over here, or you can have them to be of equal strength. Okay, so in the case when you have them of equal strength, so I have a parameter over here that's essentially the inverse of the angle up to some factor. So 0.6 in these units is about 1 degree. Okay, so this is 1 degree. This is twice of this, which is half the angle, half a degree, and so on. Okay, so you can see in this original calculation, which spurred the experiments, you have a very flat band over here, but the other bands come pretty close. Okay, and but then the other angles where you know, these are also claimed to be magic angles, where you have small velocity. Actually, the dispersion is not that small. Okay, so but you know, this looks like a bit of a mess, but you can see there's a nearly flat band. Okay, so you can contrast that with this model, the chiral model, where you have chiral symmetry, and there, once you switch off this AA coupling, you see a very clear flat band, separated out from everything else, and this keeps repeating. There are a sequence of angles at which you get these flat bands. Okay, and there's a periodicity. Actually, it's 3 halves in these units where you get these flat bands. So it predicts some higher magic angles. They're smaller angles, but there's a sequence that this model predicts. Yeah, actually, that sequence is slightly different from this one.
What units are those? Those radians or degrees?
So for alpha?
Yeah.
So it's an inverse of the angle. Actually, I think I may have missed this this slide.
Now units of the interlayer hopping.
Yes, yeah. So if you just look at, you know, so there's a dimensionless ratio that you can make, which is W divided by right? So we said that when this interlayer hopping strength is comparable to the angle times this energy scale, that's when interesting stuff happens, right? So in fact, this model that we wrote down, you can scale things away and you can show that this is the only dimensionless coupling in the model. Okay, so you can write everything in terms of this dimensionless coupling. The angle is very small, this coupling is large. Okay, there's a dramatic effect on the graphene band structure by the Moiré lattice. So the conversion roughly is, I don't know the exact number, I think 0.6 for alpha is about 1 degree. Okay, it's an inverse relationship, of course. Okay, so one question you can ask, which is what we asked, and that led us to some quite interesting consideration, is how flat is this band? Okay, it looks very flat, but what I'll show you is that it's perfectly flat. You can show the dispersion is exactly 0. It's not true in this model, and we have an analytic way of understanding the flatness of this band. Okay, so I think that I'll talk about that in a little more detail, but I think this is the best way to think about this magic angle phenomenon. There's a limit, there's a model where you get exact flatness. And you can analytically understand that flatness, and then you can think of perturbing that by more realistic coupling, some W naught, etc. And that is robust, okay? And that feature is robust. Yeah.
The flatness of the band, can we think of it as some sort of destructive interference?
Yeah, that's right. Yeah, it's some destructive interference that is preventing the propagation of some wave packet of these electrons. But if you try to unpackage that in more detail, what are the ingredients that lead to this destructive interference? We'll see some of the ingredients related to symmetry and so on, and the original graphene band structure, but we have discovered some more aspects to that which are not very obvious why they are necessary. So for example, this non-abelian vector potential I talked about, if you make it abelian, by having a potential that's symmetric in a certain way, you lose this destructive interference. That part we don't have a simple understanding. But we have an analytic way of understanding this. For the given model, we can understand why you get a zero mode or this flat band. Okay, so let me actually show you this in terms of pictures. So this is the model without the chiral symmetry, strong equal coupling between AA and AB sites. So if you're at a large angle, small alpha, so by that conversion, this is some it's some factor of 6, a few degrees, some 6 degrees or something like that. You basically see the graphene dispersions, right? It's very little reconstruction. And now let me run this, and as you get towards this magic angle, you see this middle band is getting very flat, and it's pretty flat at the end, but the other bands are following it. Okay, so and then you continue, you lose that flatness. So there was a optimal angle there, and then you get back. There's some complicated evolution after that. It's not clear if there's a second magic angle where things are flat. You can use some other criterion like low velocity over here to be try to diagnose something like a magic angle. Okay, so now let's shift to this chiral model. Okay, and again I start with this relatively large angle, and let's sort of run it, lower the twist or raise this alpha, and approach this magic angle. Okay, so here the band is well separated out, and that's the first magic angle. Okay, so it's extremely flat, and then it continues, and at some lower angle, I think this angle is about 4 times larger than the first one. Angle is 4 times smaller than the first one. You get the second magic angle, again perfectly flat band. And there's always a big gap. In fact, at those magic angles, you get the maximum gap to the other bands as well. Okay, and then there's a third one, and there's sort of a periodicity in these magic angles.
Topologies change from one magic angle to the other?
No, the topology is the same.
But the bands do touch.
They do
necessary
touch.
that they touched?
That's a good question, actually. I'm not sure.
I don't know.
Yeah.
So topology didn't change.
Yeah.
But I
this,
noticed they always touched between them.
right. Yeah.
Okay.
Yeah.
So
They don't exchange that whatever that they might have exchanged.
maybe there's something they exchanged.
There may be something else that, yeah, like some quantum numbers may be different. That we have to check. Some of the symmetric quantum numbers may be different. Yeah, so now to tell you that this magic angle phenomenon is not guaranteed, let me think of a third model where you do this kind of perverse thing of switching off the A-B hopping and keep just the A-A hopping. Okay, so this is kind of the anti-chiral model where you say just the triangular lattice science, that's where the hopping is present. Okay, and so this brings out the fact that this estimate we made for the magic angle, we balance these ratios. That's really just dimensional analysis. Okay, it doesn't tell you something's going to happen. If something happens, it's around that point. Okay, so you can see here, as you lower the angle, this these bands are never very flat. Okay, they evolve in some way. You're crossed what was previously the first magic angle. There's all kinds of evolution, but you don't see this phenomenon where things become very flat.
Never opened a gap.
They never open a gap as well, yeah. So the fact that you have this chiral symmetry seems to be relevant. Okay, if you start in the opposite limit, you won't see any of this phenomenon. Okay, so it's good to study the model in this fully symmetric limit as a way to understand this phenomenon. Okay, so let me try to convince you why you have this perfectly flat band at particular angles. So this is the most kind of technical part of this talk. So if you don't want to, if you don't want to be bothered by the details, you can check your Facebook and so on. Okay, so we had this Hamiltonian where we had just off-diagonal components. There was a D and a D dagger. Usually when you have a Hamiltonian like that, you don't try to solve this eigenvalue equation with just the off-diagonal component. Okay, that's not even a Hermitian matrix. The only reason you would want to do that is if you're looking for a zero energy state. Okay, so if you have a zero energy state, if you solve this equation, it actually gives you a zero mode of the entire Hamiltonian. Okay, so if you're looking for this perfectly flat bands, it's good to try and solve this equation and demand, ask if it has a solution where the entire band is going to be flat and the solutions of this equation. Okay, so that's what this equation looks like. You have the Dirac operator, just the derivative operator on the z bars, and this coupling u, which is like this non-abelian vector potential. Okay, now it turns out that if you're at the k points of the Brillouin zone, you're actually guaranteed to get a zero mode. If you remember that evolution we had, at the k points where you descend from the original Dirac point, those band touchings are guaranteed to be at zero energy in this chiral model. Okay, and there's like an index theorem that you can use to prove that, or just say that you have a zero energy state in a model that is chirally symmetric. And once you have a zero energy state, you cannot move that up or down, because if you moved it in either direction, there should be a partner on the other side. Even odd number of levels, you can't move it. Okay, so you're guaranteed zero modes over here. What is surprising is that you get a completely flat band. Okay, not just those points, everything in between is flat as well. Okay, so that is the thing that you want to show. So we start with this assumption that you have a solution to this equation, where at this k point you have a zero energy state. Okay, the question is, given that solution, can you build solutions for other wave vectors, which are also at zero energy? Okay, now it actually, if you kind of stare at this equation, it looks like you can. Okay, because given one solution, it looks like you can produce another solution which has zero energy by just multiplying by a analytic function. If I multiply by f of z and I plug it into this equation, these derivatives just go right through the f of z. Right, so if this thing is a solution, then if you multiply by f of z, that's also a solution. So there are many solutions that come out of this single one for every analytic function. Okay, the question really is this a valid solution to the problem? Okay, so for a solution to this problem, for this block Hamiltonian, this function should be a periodic function of position. Okay, so if I translate by a Moiré vector, it should be some wave vector k times some periodic function. Okay, so the question is, can you arrange for these periodic functions to come out? And it turns out that a periodic function to get periodicity from an analytic function, you can't really do that if it's holomorphic. Okay, so if it's just some polynomial of z's without any poles, you cannot do that. An analytic function without any poles, the only periodic analytic function without poles is the constant function. Okay, so in order to get these to be valid periodic functions, you need to have poles.
Actually, the right-hand side doesn't depend on small k1 or k2.
Yes, that will be fixed by choosing the appropriate f of k, f of 0. Yeah. Okay, so it turns out this f has to have poles, and once it has poles, it's going to be a problem because then you may not be able to normalize this solution. Okay, so the way in which you can actually get solutions using this this procedure is to have some cancellation to occur. Okay. Okay, so the appropriate functions which you need to multiply by in order to get valid block wave functions over here turn out to be a ratio of these theta functions. Okay, so these theta functions are well-known analytic functions. You can think of them as being a Gaussian, which is shifted and added to itself. And it has these indices, so these denote the location of the zeros of the theta function. Okay, and when you take the ratio of two of them, this has both zeros and poles. Okay, by appropriately choosing these indices, you can get the required periodicity, any periodicity that you like, but then it comes at the cost of introducing these poles. So what do you do about the poles of this function? Well, one thing you can do is to have the wave function over here, the thing you're multiplying it by, have a 0 at precisely the point where there's a pole. If you can do that, then this whole thing is a valid wave function, but it requires this thing to be 0 somewhere. And a priori, it looks hard to get a 0. This is two complex numbers. Okay, so you'll have to have two complex numbers going to 0 at a particular point in the Brillouin zone as you tune this angle. Okay, and that's really where symmetry helps you. It turns out there are certain points in this Brillouin zone where this wave function is a single component real number. Okay, that's these those are these yellow and green points. Okay, so at these points in the Brillouin zone, in real space. Sorry, yeah. These points in the unit cell. In the Moiré unit cell. That's right. So this is the tiny atomic lattice underneath, and this is the Moiré unit cell. And these points in real space, this wave function is a single real number, a single component real number. Okay, or you can make it a single component real number, and then as you vary a parameter, which is this alpha, this real number could change sign. Okay, and then if it hits 0, the point at which it hits 0, immediately this whole bunch of functions become valid wave functions. Okay, you'll arrange that this denominator is sitting, the root of the denominator is sitting right at that position, at this yellow point, for example, and then you can vary these parameters and get wave functions through the entire band. Okay, and that's exactly what happens as you as you vary the angle. Okay, so this is in detail what this wave function looks like. You set this theta function to be the zeros to be at these points, and this argument like this in order to get the right periodicity. Okay, so there's an interesting connection between this and the Landau levels on a torus. Okay, so a completely different problem. You have an electron in a magnetic field. You take periodic boundary conditions with 1 unit of flux quantum, ask what is the wave function. Okay, and it turns out the same theta functions appear. There's something up front which is different, which is really the ratio of these two terms, similar to the ratio of these two terms. Okay, but this operational part, this theta function is the same, and in fact, yeah, let me see if I have that. Yeah, so this is really the origin of these of this flat band. Okay, so as you tune a parameter, you can have the 0 leading to this completely flat band. And when they are flat, these bands are actually eigenstates of the chirality operator. Okay, so they live on either the side A or the side B, and they have the same energy. Okay, another thing you can show is that the similarity to this Landau level wave function or in another way, you can show that those bands have churn number. Okay, so they have this invariant we talked about last time, two-dimensional invariant. The one that lives, for example, on the A sublattice has one churn number, let's say +1, and the wave function that lives on the B sublattice has the opposite churn number. Okay, so this that goes back to the statement that these two flat bands, they have the topology of a pair of lambda levels with opposite churn number. Okay, and these don't quite cancel each other. The symmetries are such that there's some remnant of that topology that that survives despite them having opposite churn number. Okay, but then you can do this thought experiment. Suppose I have this system with these two opposite churn numbers on the two sublattices. If I added a potential that's different on the two sublattices, something on the A, something else on the B, and I separate out these bands, they would actually have churn number. Okay, and the one way to do that is to take a substrate which has different atoms on the two sublattices and bring that substrate close to this system. Okay, and that will split this AB sublattice symmetry and lead to bands that have churn number. Okay, now there's a further step that you need to do to get some interesting effect like a churn insulator. You need all the electrons to sit in one valley and pick one of these bands. Okay, but interactions can do that for you. It's like a ferromagnet where you pick one of the two valleys and then you just fill one of the bands that have churn number. Okay, so what you expect is at a filling of one quarter essentially. So when you fill only one of these four bands, you expect to get this kind of physics when you bring the substrate close to it. Okay, and that's exactly what is done in this particular paper. Recently came out in Andrea Young's group. They took this twisted bilayer graphene close to the magic angle, brought a boron nitride substrate and carefully aligned the boron nitride to give you this gap, this AB sublattice breaking. Okay, and they saw the quantized Hall effect. So this is the Hall effect. That's the quantized value. And you see that it's pretty close if you're at the right filling where this spontaneously forms by breaking time reversal spontaneously and picking one of these two valleys. And they say that it saturates and it's pretty close to the quantum of resistance, or the von Klitzing constant. Okay, so that's sort of a consequence, if you like, of this band topology, this sandwich of two opposite chirality lambda levels. You're able to separate them out. It's very easy to see the band topology because it's just regular churn number, and you just have to arrange for things, for the conditions to be right so that you just occupy one of them. Okay, so, but what happens in this bilayer graphene is that both those bands are present and they're kind of stuck together. You've not broken this C2, you've not broken this AB sublattice symmetry, and somehow that is responsible, we believe, for all the interesting stuff that happens, which is different from this quantized Hall effect. Okay, so let's get back to how good this model is, this chiral model for a real system where you have both of these couplings, both the AA and the AB coupling. So this is a plot of, let's say, the band gap to this isolated band near the magic angle as a function of the ratio of this coupling. Okay, it's maximum when there is no AA coupling. And then as you go to this limit of equal strength, this McDonald model, that band gap closes. Okay, but in reality, it turns out people have done first principles calculation, think that the right value to use for this ratio is something like 0.7. Okay, where you seem to be continuously connected to this chiral limit. Okay, there's no other band coming nearby. And so those wave functions smoothly evolve into this. So it's a good starting point, we think, to understand actual twisted bilayer graphene, where you're not quite on this limit, but you're somewhere in between. Let me just check how much time do I have? Another 15 minutes, is it?
Yeah, we have a little bit more because we started late.
Okay, yeah. Okay, so so one aside, let me mention, which is kind of interesting to think about. So once you have this chiral model, it's a very clean model to try other configurations. Okay, so you can try it in the chiral model and then put back the true couplings once you identify if there's something interesting happening. Okay, so one thing we did, which was the idea of one of our postdocs in the group, Islam, was we took a tri-layer sandwich of graphene and imagine twisting the middle layer. Okay, so it's just a single layer twisted, and let's say the top and bottom layers are in registry. So this is kind of the configuration. Or you could take 4 layers and twist the alternate ones twisted by theta minus theta. So you just have a single, so there's a single twist, it just alternates in sign. And you can think of many layers in this way. And so we can ask if there's something interesting that happens there. So it turns out one of the reasons to look at this model is that it's actually trivial to solve. You can just map it back to the model of to the 2-layer model, and the magic angles that you get in these other situations are simply related to the original magic angle. So 2-layer has a certain sequence of magic angles. The 3-layer case, there's another sequence, and they're related to the original ones by a factor of square root of 2. Okay, so that's kind of good because it means a slightly larger magic angle, maybe easier to make, and maybe easier to, you'll have stronger interactions if you have a somewhat larger magic angle. If you do 3 layers, again, you get a sequence. They kind of double, the number of magic angles sort of doubles, and the ratio is now the golden mean compared to the original bilayer case. Okay, so let me just show you this 3-layer case because we think it's kind of promising. So one additional thing that happens in the 3-layer case is you have this very flat band when you tune to the new magic angle, but there's sort of a remnant of the 3rd layer, which is a Dirac cone. Okay, so you have a nearly flat band and this very rapidly dispersing Dirac cone that intersects them. Okay, so it's not as clean as just having a flat band, but maybe this is a situation where you get some interesting physics from the interplay of this very fast moving electron and these other electrons that barely move around. Okay, so we hope that this is something the experimentalists can look for. Yeah, question.
Are there things that can be said using these models for other stacking types like no angle and then, I mean 3 different sheets, but then the top one on the rotate?
Yeah, you can certainly do that. I'm just trying to think if it's obvious what the answer is.
Because I know some experiments have been done.
Yeah, I can't quite tell. There's a recent paper by Alan McDonald, which I didn't cite, which they tried different, maybe they tried that one. Yeah, offhand, I don't know the answer to that. Islam may actually know the answer. Okay, so in the last part, let me just tell you a little bit about our efforts to write down a tight binding model and what the problem is with the naive way of trying to write down tight binding model. Okay, so what you'd really like to do is to write down a model just for these 2 bands. So a model with just 2 sites in the unit cell, and if you solve that, you'll be able to find bands that preserve all the symmetries. You don't want to give up on symmetry for a single valley. Okay, so for each valley, you would like to write down just a 2-site tight binding model that will capture this flat band. Okay, it turns out that's impossible. Okay, and let me tell you why. So different ways of thinking about it, but this is the most kind of, at least physical way for us. If you just examine the chirality of the Dirac points, how these wave functions wind around these 2 points, it turns out that they both have the same chirality. Okay, and you actually have enough symmetry to define this chirality properly. You have the C2 rotation symmetry by 180 degrees. It turns out that if you had any band structure, if you had one with, coming from some tight binding model, these 2 would have opposite chirality. In fact, that's what happens in graphene. You have 2 Dirac points, but they have opposite chirality. In this case, because they descend from the graphene Dirac points in 2 layers, they actually have the same chirality. Okay, and you can show that this cannot come out of a tight binding model. Okay, let me give you an argument why. It's kind of related to this, this topology of the band again. So imagine this is sort of a proof by contradiction. Imagine there was some model where you just had 2 sites in the unit cell, and you magically got this band structure, okay, with the 2 Dirac points with the same chirality. Okay, and now what we're going to do is in this just 2-site model, let's imagine you add a staggered potential. Okay, so the staggered potential will translate into a mass term for the Dirac fermions, but the mass term will be the same sign for the 2 Dirac fermions. Okay, it's independent of momentum, it's just some staggered potential inside the unit cell. Okay, so you get the same mass term for the 2 Dirac fermions, but now because they're same chirality, this will end up giving you a Chern number. Okay, you'll get Chern number 1 for this band. Okay, but it's impossible to get that from a staggered potential, and the way you can argue that is that if you make the staggered potential very large, all the electrons are going to go into the negative potential site. Okay, which means that you've just gotten a Chern number from an insulator that's completely trivial, right? The electrons just sitting on a site, yet you ended up with a band that has Chern number. Okay, that can't happen. We know there's no Vanier description of a Chern insulator. It certainly cannot come from something where the electrons just sit on, say, the blue sites. Okay, so just a two-band model where the only operational things are these two sites, where you can make this sort of extreme potential argument, cannot give you this Chern number. Okay, so what are your options? If you have to give up on this two-band model, basically, right? So what options do you have? Actually, let me just come back to the slide a little later. The options that you have are, one is you can lose some symmetry. Okay, you can write down a tight binding model where you don't have some symmetry. For example, you can lose the valley symmetry. The model doesn't explicitly have valley symmetry. It combines two Dirac points here and two Dirac points from the other side, which have net chirality 0. So we try to do that. Other people have tried to lose this 180-degree rotation symmetry that protects the Dirac points. Try to write down some tight binding model. But clearly what is important is you want to keep the symmetry, right? Because you don't have symmetry, you don't know exactly what terms to write down. There's some complicated check you have to make to know whether what you did broke the symmetry or not. Okay, so the other option turns out to extend the model. Okay, so you can include more bands. And the sole purpose of these bands will be to give you the right topology. Okay, so it's fully symmetric. These Dirac points will be preserved, and actually you can use it to your advantage. These extra bands could actually be the excited bands of the model. Okay, so you can, the regime of validity of this model can extend beyond the flat band and include some of these excited bands. And one slightly technical point is that the extra bands actually do not carry any topology. They're like trivial bands. They're just some additional sites that you need to put in, which is what we call this fragile topology. It's not like Chern number, where when you have a Chern number band, you must supply the opposite Chern number band. Okay, here we're just going to add some, some sites which will, remedy the problem with making this tight binding model and end up giving you the bands of interest. Okay, so let me actually just conclude with just report this thing. So we have managed to do this, starting with the calculated tight binding, the calculated band structure. We have been able to write down these, not just write down tight binding model, but actually find wave functions, so-called Vanier functions. The hopping between those sites, those Vanier functions end up reproducing the band structure and the topology of those bands. Okay, so really it's a unitary transformation. What we're doing is you're selecting a window over here of bands, and actually the chiral model helped us over here to cut out a bunch of bands that are separated from the rest. You make a unitary transformation so that you end up with wave functions in real space. Those are the Vanier functions. And then you can rewrite all of the Hamiltonian over here, making the same unitary transformation, as some hopping between these localized orbitals. Okay, and so the minimal number of bands you seem to need to reproduce this physics and be realistic, get the things nearby, is a 5-band model. Okay, so there are 2 bands over here, the flat bands, and then some additional bands, excited bands that have to be included. Okay, and this is what this model looks like. It has orbitals on the triangular lattice site, on this AA site, 2 orbitals. You can think of them as like the symmetries are those of a px and py orbital. And then there are these additional actually, sorry, there are 3.
3 on the A's. 1, 2, and 3.
Yeah, sorry, I'm getting yes. There are 3 on the AA sides, that's right, thanks. Yeah, so this is like the px and py orbitals, and there's a pz as well. I mean, it has symmetry of a pz orbital. All of these are on the triangular lattice sites, and then there are 2 others which are on the honeycomb lattice sites. Okay, the AB sites. That's a 5-band model. If you want to be symmetric, you can write down one with 8 bands, which has both the top and bottom. That includes the so-called Kagome sites, which are the centers of this of the bonds connecting the triangles. Okay, and once you have this, you can also do the unitary transformation to the interactions and get something like a Hubbard model. Okay, and that's presumably the next step. That
So if you didn't want these other bands to be realistic, could you have done it with a 3-band model?
Gotten the right symmetry for the two bands you want?
You can't do it with the 3-band model.
You're sure?
Yeah. You can do it with 4 bands where
Four is the minimum.
4 is the minimum, yeah.
It's not realistic.
Yeah, so what you do in the 4-band is you literally cancel the topology of this one with the opposite one. Yeah, but there's nothing in the spectrum like that. Yeah, but you can do it with 4, yeah, if you're, yeah, but this 5 is really the one that, yeah, and actually the interaction strength is not that much smaller than the band gap. So you may actually have to do this 5. Okay, so yeah, so anyway, this captures the band structure and you can decompose it into the weight on the different orbitals. It's pretty much all on the triangular lattice side, this 2 px and py orbital, except there's a little bit at this gamma point where it misses it. Okay, so this plot, what it's doing is it's taking the band that is in the band structure and looking at the overlap with the different orbitals. Okay, so people often do that in band structure. So you get some, a lot of the weight can be captured by the px and py orbital on the triangular lattice, except at this near the gamma point where the overlap is 0. Okay, so that's why you cannot do it with just those 2 orbitals. There's some topological obstruction which makes this vanish at the gamma point. So to patch up that gamma point, that's where all these guys come in. Right? You need this whole entourage of bands to patch up the weight at the gamma point.
The DW is the Kagame site?
Yeah. Domain wall, because it's some domain, it's thought of as a domain wall, yeah. Okay, so I think I'm out of time, so let me end over there. So maybe the main message over here is, there's something extremely interesting and mysterious to some extent about these flat bands of this magic angle graphene. We have found some of these aspects of it, the topological aspects. There are many things we don't understand. Okay, so one of the things we don't understand is there's a periodicity of the magic angles in our model. There's a period in alpha of 3 halves. Okay, so every 3 when you shift by 3 halves, you get another magic angle. And we don't have a simple way of understanding that. Okay, we also don't know why you need this non-abelian nature of this potential in order to get these flat bands. And that's sort of on the more formal side. On the phenomenological side, we really don't understand this system. The way in which we understand even the cuprates, we don't have the similar kind of understanding of these insulators and superconductors in magic angle graphene. Okay, in cuprates, we are pretty sure it's a D-wave superconductor. We don't have the analogous answer for the superconductivity in magic angle graphene. The insulator and the cuprates we know is antiferromagnetically ordered. We have no idea what the insulating states are for example, in Pablo's experiment. So on the phenomenological side, it's completely open, I think. And hopefully some of this interesting physics of the bands is reflected in the interacting physics. Okay, I'll stop there.
There's a couple minutes for questions.
Going back to the 0 mode that you started off with, is it fair to think of it as an infinite number of 0 modes?
Yeah, that's right. In a big system, the number of k points is infinite.
So what happened to the index theorem then?
So we don't have a way of understanding all the 0 modes within the index theorem. The index theorem only applies to 2 points in the Bilworth zone, the way we are. Because those 2 points, regardless of the angle, you have a 0 energy state. So then you can just apply some index theorem and it gives you that. The thing that's unusual about the 0 modes is it happens at a precise value of the angle. So it cannot be some general theorem that guarantees it everywhere. It has to know about the angle. Yeah.
How large is the vicinity of the gamma point where these other orbitals kick in? And do you expect some kind of filling where essentially the orbital character of this flat band changes and maybe there would be some different interaction effects? Do you expect that when you hit the states at the bottom of the near the gamma point?
Yeah, so there's no real scale because it's probably like a vortex, right? So you have this overlap, which is probably like k or k. So I don't know actually what the overlap, how it goes to 0, but it's some function of either k or k squared. So it's no real scale. It's just it goes to 0 algebraically. But whether that has some effect, that's an interesting question actually. Whether when you're at very low filling, the fact that it's on some other site may be important. So it's true that if people who do STM, like Ali and other people, most of the charge density lives on the triangular lattice site, which is kind of consistent with this. But you empty it and fill it, the charge density changes on the triangular lattice site. Most of the weight is on the triangular lattice site. There are some phenomena that you see that may be reflecting this, at least in calculations. If most of the charge density is on the triangular lattice site, you may want to move to the gamma point to avoid interactions, right, and things like that. But I don't have a very good answer to your question, whether just from these plots I can make some prediction for small filling where you're near the gamma point.
Yeah, so it's tempting to think of this as a kind of SU2 analog of Landau levels, right? But the non-abelian field strength is not constant here, right?
Yeah, it's not.
Some complicated oscillating function.
That's right, yeah.
And it's very important that it's exactly that, right? Otherwise it goes away, right?
Yeah, it has to be non-abelian, but you give me any non-abelian function, it will have 0 modes. You need to ensure that it's threefold symmetric, because you use that to get a 0 somewhere, function of one parameter. But apart from that, it's just got to have both components, both the x and y component. It has to have the right symmetry, and you'll get some 0 mode somewhere at some angle.
But to get the flat band, you need something more, right?
No, so this 0 mode condition just gives you the flat band. Once you're at 0 at some point in the real space wave function, that entire band just
you can adjust the angle then.
Yeah, you just adjust one parameter to get the 0. So one difference from Landau levels is Landau levels, everything is flat. Not just the lowest line, every Landau level is flat. So here, just the 0 mode band is flat. So in terms of algebra, you may ask, is there an algebra like the lowest Landau level algebra that guarantees the flatness? So you can't have that kind of algebra over here. There's something like that you can write down, something like this magnetic translations, but it's only valid for 0 energy states. So there's some analogy to Landau levels, but it's not perfect. Yeah.
So you didn't say much about the interactions. So you have an 8-band model or a 5-band model, and now you've got interactions. Do you know anything about those interactions yet that's interesting to say?
So, in principle, we have this unitary transformation to go from momentum space to real space. So, it's a question of calculating those integrals. So
you haven't made much sense of it yet?
We have not done the calculation yet. It's a project, right? I mean, you can try to guess and say, oh, the interactions are probably mainly on this triangle lattice sites, right? Some Hubbard-like interaction. Most of the charge density is sitting there. You can make some guess like that. But if you want to be careful, and there are probably going to be all kinds of terms, not just density. There's going to be pair hopping interactions and things like that. And those are actually important for questions like superfluid density and stuff like that. It's not just the bandwidth or the band dispersion is giving you, but even like the topology of the band is giving you superfluid density. These interactions can also contribute to that. So yeah, we'd like to do it a little carefully. Underway, yeah. So this was done with Stephen Carr, who was and Adrian Poe.
So we have this parameter that you mentioned that's tuned between the chiral and anti-chiral limit. Does it have any effect on all this results that we have?
Yeah, so this is for the so-called realistic parameter, where you take the actual mechanical relaxation of these things, calculate that, and use that value to get this band structure. You could try to do it at the chiral limit. We have not tried to do that. We use the chiral model actually to separate out these bands. So it's actually useful, because if you look at the actual band structure, there's no simple way to stop at 5 bands. You don't really know where to cut it off over here. So in the chiral model, it's nicely separated out. There's 2 and 3, and you can use the projection of that onto this to identify some 3 bands. And then you can use that in making linear functions. But you could do the same procedure for the chiral model and see something simple coming out.
Okay, let's thank Professor Vishwanath again.